So before we look at the main theme of today, which is solving exponential and log equations, I thought we should probably try to shore up our log properties a little bit more. So we're going to look at these first three and see if they're true or false. If you're watching the video, you might want to try and see if you can decide on those and give a reasonable explanation first and pause the video. So what do you guys think? The first one, true or false?
True.
Ah, you guys are just like my first hour class. The first one is false. Okay, if you don't believe it, can we use the calculator to see if it looks like it's false? Let's do it. So I'm going to type the left-hand side. If they're equal, the left is supposed to equal the right, right? These are nice log base 10, so easy to put in our calculator. So log of 40 minus log of 10. That's about 0.6, okay? If you do log of 40 divided by log of 10, it's not 0.6. It's 1.6 something. Clearly not the same, right? This is not true. That's one of the most common mistakes I see students make in logland. Why is it not true? So your instinct, most of you said true. I know that's because you're starting to have an instinct, which is good. Your instinct said, well, minus in logland becomes division. Is that instinct wrong? No. Except you've got to refine it a little bit more. Yeah, see, let's refine that instinct. Yes, minus becomes division in logland, but you've got to have more to it than that. The idea is that two logs that are subtracted become 1 with division inside that 1. There's not 1 here, there's 2. So what would have been the true statement here is if you'd said log of 40 minus log of 10 equals 1 log of 40 divided by 10, which is in other words the log of 4. If you do the log of 4, log base 10 of 4 is 0.6, and you can see that those match. So notice, you can't just be super reflexy here. It's good to have reflexes that say minus become division, but it's 2 logs that become 1 as well. You can't pervert that into some other type of arrangement, okay? So it's so easy to make that mistake. I know I did it when I was your age. So just thought I'd point that out. Gets almost everybody. Second one, what'd you guys think on that one? True or false?
True.
True? There's crazy stuff in there though. Like 128 over 65, 2.5, 13. Somehow this is all just equal to 6?
It's too crazy not to.
I was hoping it would be you'd look at it and be like, it's too crazy, it can't be 6. These are all log base 2 though, right? So can you put them together into 1? Yeah? Plus in each case becomes multiplication, so you can say that's 1 log out of the 3, where you have 13 times 2.5 times this fraction. Multiply all that stuff together, see what you get. Let's do it. So I'm hoping this is what you guys did. Careful with my fraction, wrapping it in parentheses. Oh, that's just 64. So it is 6. That's true. It's 2 to the 6th power, 64. So there we go. So you can't just look at something and be like, whoa, it's ugly. It can't simplify to something nice. That can happen. It just happened. What do you guys think about this last one for our warm-up examples for today? True, false? It is false. Part of it's good, part of it's not so good. What part of it's good?
The log base 3.
Yes, the log base 3 of 48 I think is the good part. But have we learned any kind of property with logarithms that says that you can be like, oh, there was a 2 in front of that one, a 3 in front of that one. So I'm just going to stick them out in front of this one. What suggests we can do that? See, there is a right way to do this problem. So let's erase this and make it true. Right now, you can't put those together, actually. Your instinct to multiply and say that that's 48 is good, like Anna said a second ago, right? That's great. But you can't yet. There's something in the way. This 3 is in the way. That 2, even though it doesn't look like it, is also in the way. This is clearly in the way, though, right? You can't do this until you move that 3 somewhere. Where can you move it? To the exponent. Thanks, Ms. Proctor. So instead of being right here, this 3 by another log property could also be Up there. Where could that 2 be? Up there. Now you can put it together with multiplication and say 2 logs become 1 log with what inside? 6 squared and times, plus becomes times 8 cubed. So this is the same thing as the log base 3 of 36 times, 8 cubed, is that 512? You guys better check me.
Yeah.
I learned my power tables, so crazy. And you guys are going to have to tell me it's that one, I don't know what that is. 512 times 36?
18,432.
You're going to see how Lindsay's on top of it? That's where you should be too. Now, I can't see if is that a power of 3? Well, of course, we don't know our powers of 3 that high. Maybe it is, maybe it isn't. So let's use our change of base formula to have this done in the calculator. So our other log property is the change of base formula. So I'm going to change that base 3 to base 10. So I go log, log, and where's the 3 go? On top or on bottom? The 3 is what I don't want, so I'm going to divide it out. That's how I remember it. If you want to remember it some other way, great, but that's my suggestion to you. Let's see what our calculator says this is. I bet it's not a power of 3. That'd be just too crazy. Nope, it's 8.9. So 3 raised to the 8.940. That's what ends up being 18,432. Okay? So, what have we learned here? Be careful about just assuming minus becomes division without thinking about the details a little more. Don't be intimidated by ugly looking stuff. It can come out nice and simple. And the last one, if you've got things down in front blocking you, unblock them. Okay? A few different strategies you need when solving exponential and logarithmic equations. So I just wanted to start out with some really simple motivation. So I think you guys should probably be able to tell me x in that first little simple equation there. What is x? 81? Square root of 81 is 9? Cool. If you were to try to solve that and not just guess it or solve it by inspection like you guys just did, I think, how would you get rid of the square root? How do you get rid of square root? Use its inverse operator, which is squaring. So you square this. If you do one side, do it to the other side. So that says that x equals 81, right? So these cancel out, and you get x equals 9 squared, which is 81. So a simple log equation can be thought of the same way. Can you guys solve that by inspection for me? Just look at it and tell me the answer. It's not hard, I mean, what is x? So log base 4 of 10 equals log base 4 of x. X equals 10. That's the only way it's going to work, right? So that's just guessing it because it's so easy. The only way these are equivalent expressions, since they're both log base 4, the only way log base 4 of x is equal to log base 4 of 10 is if 10 is x. That's it, right? But how can you think about it with an operator? We learned that last week that the inverse operation of logarithm is what? We graphed it on the board over here. I think we flipped it like over the line y equals x. We saw that logarithms and what other function are inverses of one another? Exponentials. Thank you, Mr. Garner. Nice. So exponentials. Exponentials the same base or different base? Well, the same base. You got to use the same tool. You got to use the right ratchet to undo a screw. You got to use the right exponential to undo a logarithm. Does that make sense? So logarithm base what should we operate with here? Base 4. So this is not multiplication, that's key. It's not multiplication. I don't multiply to get rid of logarithms. I multiply to get rid of division. To get rid of logarithms, I operate with an exponential function with the same base. So the exponential function with the same base is 4 to the x power. So I'm going to exponential both sides with base 4. If I do it on one side, I've got to do it to the other side. Make your exponential bases real big so that you clearly see it's an exponential, not multiplying. It's not multiplying. That cancels, and we get 10 equals x, just like we already knew by inspection. Okay? So we're going to use that same principle. That's really the only theoretical idea that we need, is that we need to remember that inverses cancel each other out, and logs and exponentials are inverses of one another. So that's really the only main idea that we need to solve some of these. There's lots of variations, though. We've got to bring together a lot of knowledge today. So this first one, you can totally approach it that way. There's an easier way, though, so I'm going to show you the easier way, because you're going to want to do that. Those bases are related to one another on problem 1. This is an exponential equation. How does 27 relate to 9? 9 times 3, yeah. How else are they related? Think about your power tables. They're both powers of 3. If they're both powers of 3 or anything else, much easier to do it that way. In fact, 9 is what power of 3? It's the second power, nice. So that's 3 squared. 27 is 3 cubed, or 3 to the third power. We've still got those x things, right? But that's the same thing, because 3 cubed is 27, 3 squared is 9. Right? Why does that help us? Well, because now we can do some exponent stuff. I heard we need to multiply the exponents. Very good. So this is going to be like 3. If you have power to power in algebra, that means multiply. That's big. That's 2 times 8 minus x, the quantity. And this is 3 times x minus 3, the quantity. Now look at that and think about it. It's very similar to that last problem we did. Yeah, I know there's no logarithms in it. You can do this 2 separate ways, just like we did a second ago. You can do it by inspection, or you can do it by operating with an inverse. The only way that these two things are equal to each other by inspection is if what? They both have the same base. There's blue 3 there on both sides. If there's a blue 3 there on both sides, do you really need the blue 3? No. So you can just erase it. If you don't like that, if you're like, whoa, it's like mysterious, disappearing stuff, it would have been me. In high school, it was definitely me. I was like, what? What are you talking about? The only way these two sides are equal to one another, because we're trying to see where they're equal, is if the exponents are equal. So you don't even need the blue 3. But if you're like, whoa, that's like too magical for me, then be a mechanic. Grab a machine. Grab a tool. What gets rid of exponentials? We just talked about it a whole bunch. Logarithms. If you have base 3, what tool do you need to pick specifically? Logarithm, base 3. If you do something to one side, like operate with a big red logarithm.
You gotta do it to the other.
Thank you, Richard. Logarithms cancel exponentials. So if that makes you happier, as it would have me in high school, then do it that way. And then you've just got a little algebra 1 easy problem left to solve. So distribute and do all your stuff. Let's see. So we're going to have 16 minus 2x, right? And 3x minus 9. Combine your x's and all that stuff. So let's see. Add 2x, that's 5x. Add 9, that's 25. So the first answer is 5. That's by far the easiest way to do that question. There's another way for sure, probably a couple other ways, but that's the easiest, I think. So another way to solve that is to use logarithms earlier. You don't have to recognize the crazy blue thing that I did. You could use logarithms earlier, but the algebra would get a lot messier. So let me show you that way on number 2. On number 2, you can't do my trick that I did on this one, because here they shared the same base of 3. They share a base on the second one. One's base 4, one's base 5. Can you rearrange those into like the same power, 4 and 5? I don't think so. It's not going to work. So instead of waiting to use logarithms, I'm just going to be like, you know what? I want to use logarithms right away. And it really doesn't even matter what tool you use here. If you want to use base 4 to get rid of the 4, great, but then you're going to have to use change of base. So I'm just going to pick a random logarithm. Like base 10. If I do it to one side, do it to the other. The key here is that you don't get intimidated by weird-looking stuff. This is a very easy algebra problem if you don't get intimidated by weird-looking stuff. That's weird-looking stuff, I know, but it's just a number, right? Log base 10 of 5 is something. It's a number. Oh, and we have a property that like lets us solve this x problem. What can you do with this thing up here? You can take this guy and put it in front. The reason you want to do that is because otherwise it's stuck up in the tree where you can't get to it, but now it's not. And once again, this is the easiest algebra problem I've ever done with you. It just looks funky. Algebra 1 kids can do this problem easily, like right now. If I instead put 4 instead of log 4, and instead put 5 instead of log 5, they can do that easily. Because those are just numbers, so don't get intimidated. If this was like x minus 1 times 3 equals 7, could you guys solve? Yeah, what would you do? You could divide by 3, or you could do what with the 3? You could distribute it. I'm going to distribute it. So this is x log of 4 minus 1 log of 4. So over here you'd have 3x minus 3 equals 7. Your next step on this one would be to do what? Add the 3. So on ours, the next step is to do what? Add the log. These are just numbers. Don't let them scare you. They're just numbers like 7 and 5. Or whatever you want them to be. They're just loggy numbers. So here I've got x log of 4 equals log of 5 plus log of 4. If you want to use log properties at this point to shove those together, you can. There's no need to. They're just numbers. But the last step over here, we would have what? 3x equals 10. Our last step over here would be divide by 3. So our last step over there is divide by that log. So going back to Kirsten's question from earlier, which I think was a really good one, are you ever going to have division with logs in it? Yeah. You just got to be careful about where things come from. I mean, lots of different things can happen. Don't try to anticipate everything that can happen. It's just too hard. So up here I'm going to have, I could use a property there even, right? Plus becomes times. You didn't have to though. I mean, you're just going to have to feed that to your calculator. What do you guys get? Can you feed that in your calculator and tell me what you get? Give me a few decimal places, please. What is that? 160 or 1?
0964.
09s, then that. Yeah? Okay, there we go. So, 2 different ways to solve exponential equations because each of these started being exponential, right? Number 1, oh, I erased it over here. But number 1 is use the same base. If they have bases that are like in the same family, rewrite them as powers of the same base. That's faster. If you can't do that, like 4 and 5, use the logarithm right away, bring the powers down, and don't get intimidated by weird-looking stuff because it's going to be an easy problem if you focus on what's variable, what's a number, and just think about like terms. It's super easy as long as you're focused on these not being crazy things. They're just numbers. Number, number, variable. Okay? That's all there is to it. We'll do another one like that tomorrow. Let's go and solve some exponential equations first, or excuse me, logarithmic equations. So I wanted to look at 2 or 3 of those. So these guys start out as logarithmic equations. The first one, number 3, is super simple. You want to solve for x, right? You want to get x by itself. It's trapped inside a jail right now. We need to get rid of that jail. How do you get rid of the log base 6 jail? Base 4. How do you get rid of logarithms? Exponentials. You got to match it, so base 6. If you guys are like, man, he's writing way too big, believe me, write big so you're clear. It's not multiplying. If you do it to one side, though.
Gotta move to the other.
Okay. So then we've got 2x minus 1 equals 6 to the negative 1 power. What's 6 to the negative 1 power? It's a 6th. And it's just easy algebra. So add 1, that's 1/6, and 6/6, so that's 7/6. And divide by 2, it's the same as multiplying by the reciprocal, right? So you're going to get 7/12. So there you go. Number 4, I'm going to need some help. I don't think we can just for it. In other words, exponential base for it right away to unlock those x's. I'm going to do something else first. Okay, so I heard someone say combine it for this one. What do you mean combine it? Yeah, you guys heard Kyle use division. He said take these two logs, they're both base 4, stick them together. 100 divided by x plus 1. We've got a property that does that. Now it's just like the last question. Unlock it. To get rid of log, use exponential. Four to the 1, 4 to the 1's just 4. We need x, there's x's on the bottom. I think you guys should remember if there's x's on the bottom, get rid of them by multiplying them up to the top. I'm going to just distribute.
So x plus 1, when you have x minus 1?
No. Because this cancels, doesn't it? Because it's 1. Something over itself is 1. So that's the move you want to make. It's a good question though. And then I just distribute it on the right hand side there. Combine your like terms and you're done. So minus 4. Divide. Might need your calculator on that one. But 100 divided by 4 is 25, so yeah, it's 24. There we go. Done deal. Let's look at one more for today and then I think we'll pause for tomorrow. Okay, so log base 5 of x to the 4th equals 8. There's two really good ways to solve this. One of them kind of requires you guys to remember something from last week. It's only the first time we've done it. So you guys tell me. Suggestions, let's see if you pick the hard way or the easy way. Well, they're both easy ways, but... Suggestions? Cameron?
Bring the x down.
Bring the what down?
The exponent.
Exponent, this guy? Smart. Good reflex. Cameron's got some reflexes going on there. I think many of you guys were thinking about that, yeah? Let's see if this requires anything clever. We want x. I can't like 5 it right now, right? I can't 5 it because there's something in the way. The 4 is in the way. How do you get it out of the way? I want to get out of the way. It's doing what to this? It's multiplying it. So divide. Divide by 4, and you get 2. Now it's not in the way, so now what can we do to break that logarithm wide open? Exponential it. So this says chop, x is 25. Now there's another way to do that, which is, I don't know, equally good, except it requires you to remember something else. Let me show you that as well. So if Cameron hadn't thought to bring that 4 down, what could you do right away? Couldn't you do that right away? And this cancels, right? Yep. You have x to the 4th power equals, oh man, I don't know that power, 5. Calculators? What you guys got? It's a big number.
390625.
390625. So 390,000. And x is still not by itself. Ugh. So for one, I didn't need a calculator over there. We already used ours once. How do you get rid of 4th power? You haven't done that too many times in your career yet. That's a good idea. You not square the square, but square root the square root. That is exactly what you guys do. You're right. Last week, we learned that what power is the same thing as square root? 1/2 power. So you can either raise this to the 1/4 power, or you can apply the 4th root. I'm going to think about the 4th root. There is a 4th root, we just haven't used it much, if at all. So the answer is the 4th root of 390,625. Now there's a couple ways to put that in your calculator. You're going to have to use it again, so you got to use it twice if you do it this way. But the easiest way is to remember what I said from last week. Square root is 1/2 power, so 4th root is 1/4 power. So that's the easiest way to put this in your calculator, is to raise it to the 1/4 or 1/4 power. So why don't you guys do that and tell me what the answer is? Better be like 25, right?
Yes. Easiest 25.
So there you go. So a little bit longer way, requiring some much bigger numbers. You definitely need a calculator for it. Equally good other than that, just some big numbers came into play. So we'll look at some more complex logarithmic equations tomorrow. So I'll see you next time.